How did our universe go from the uniform, structureless reality of the Big Bang to the place we see today, filled with stars and planets and galaxy clusters? Today we're going to tell this story, the story of how large-scale structure evolved in our universe, and all the different players that had a role in shaping essentially the skeleton of the world around us. You're listening to Why This Universe, a podcast where we break down the biggest ideas in physics. I'm Shalma Wegsman.
And I'm Dan Hooper.
Today we're telling the story of how our universe evolved to form large-scale structure. So let's start our story at the beginning, or at least the furthest back that we can go. Our oldest picture of the universe comes from the cosmic microwave background, or the CMB. This faint background of light preserves a picture of the universe from just about 385,000 years after the Big Bang. When we look at this picture, we see a very uniform and pretty boring universe. Now, the universe was extremely hot back then, but the time that light from the CMB reaches us, it's a lot colder, 2.7 degrees above absolute zero, to be more precise. That's because space has been expanding as this light has been traveling through it, causing the photons from the early universe to stretch out and become much lower in frequency.
It's kind of like if you take a piece of music, a recording or something, and instead of playing it at the proper speed, you play the record at a slow speed. Right, so all that information is still there, basically, but it's way, way, way lower frequency, or in this case, lower temperature.
Looking around the whole sky, the temperature of the CMB varies extremely little from this average temperature.
So in every direction, if you point your CMB telescope in every direction, you see essentially the same temperature, 2.725 degrees above absolute zero. And the hottest and coldest spots of that sky are different from the average value only in about like 1 part in 10 to the 5. So this is about as uniform as anything you can find in nature. These tiny little temperature variations we see come from the fact that the density of our universe early on had some variations in it too. Again, 1 part in 10 to the 5. So if you're a little bit of light and you start out in somewhere in the universe with a little more density than average, gravity pulls on you as you try to escape, and that cools your light, making it appear like a cold spot in the CMB. And hot spots are places that had a little less density than average. So by looking at the CMB, we're really getting a map of the density variations in our universe 380,000 years after the Big Bang.
This is just the beginning of our story of structure formation. We start from these tiny variations in density that are just 1 part in 100,000 different from average. We can't know for sure what caused these variations, since the cosmic microwave background is the first signal that we get from the early universe, but in many ways these tiny variations planted the seed for what would become everything of structure in our universe today. So, winding the clock forward, we'll see how these tiny differences snowball thanks to the hands of gravity.
Imagine there's some region somewhere that has just a little bit more density than average. Maybe this is one of those cold spots in the CMB that's 1 part in 10 to the 5 colder or higher density than other places. Since every bit of matter and energy pulls on every other through the attractive force of gravity, and since there's more matter and energy in this overdense region than in others, gravity will tend to pull particles toward the center of this region, and that will make this overdensity become smaller and more compact. In other words, it will become increasingly dense, at least relative to the other parts of the universe as time goes on. If you do the math to figure out how a small overdensity will evolve with time, you'll find not only will gravity cause the overdensity to collapse, but it will cause it to collapse at an exponential rate.
It all starts with a small overdensity, which causes stuff to get pulled together more, which causes an even more dense region, which causes even more stuff to get pulled together. It's all one big gravity snowball.
So how long it takes for an overdensity to grow exponentially depends on the density of the substance in question. So higher density environments cause clumps to form more quickly than lower density environments do. When the CMB was forming, for example, these regions were collapsing on a time scale of around 100,000 years. So every 100,000 years or so, these density variations were increasing by a factor like 2 or 3. And that would happen every 100,000 years. So it just kind of gets bigger and bigger and bigger.
Now, this can't be totally correct. Think about it. If all overdensities in the universe were always getting exponentially denser, what would you expect to happen to the Earth, for example? I mean, the Earth is a huge overdensity compared to most places in the universe today, and yet it doesn't appear to be collapsing in on itself exponentially. It actually appears pretty stable. To see what's going on, let's take another, more simple example.
So if I take something like my cup of coffee that I have sitting on the table in front of me, I find that the density variations in that coffee should grow exponentially at a time scale of about 20 minutes. So if I let my coffee to sit there for an hour, this math says it should turn, instead of being a smooth, liquid, it should be a whole bunch of just like kind of dense clumps of coffee. And that's not what happens, all right? We all know that's not what's going on, especially on any reasonable timescale. And the reason is that gravity isn't the only force at play when it comes to my coffee or to other stuff we experience, like in our normal everyday lives. In addition to gravity, the atoms in my coffee are moving around pretty quickly, and they provide pressure that helps to prevent these density variations from forming. If I push some atoms of coffee together in a small volume, they bounce off each other more and they push out, restoring something like the homogeneous fluid that is in my coffee cup right now. So there's kind of a competition between the effects of gravity and pressure. And it turns out that which of these forces win depends a lot on how big the overdensities or the clumps we're talking about are. In our day-to-day experience, we mostly deal with small things like cups of coffee. And on small scales, gravity almost never wins. Okay, so pressure, at least for ordinary stuff, can prevent my cup of coffee or whatever from collapsing into gravitational clumps. But as you get to bigger and bigger things, gravity tends to increasingly win out over the effects of pressure. At the time that the CMB was forming, for example, pressure would win out over gravity for any like clouds of gas or other stuff that were smaller than about 200,000 solar masses. So something 200,000 times as massive as the sun. Things smaller than that would do very little because of the effects of pressure, while things bigger than that would still collapse and form things like small galaxies or even big galaxies, eventually stars, etc., etc., etc.
There's a missing piece of this puzzle too, something that has had a huge impact on structure formation in our universe that you might not expect, and that's dark matter.
As listeners to Why This Universe probably already know, atoms don't make all of the matter in our universe. Instead, most of the matter in our universe consists of what we call dark matter. We don't know what it is. It doesn't radiate, reflect, or absorb light in any noticeable way, but it makes up most of the matter in our universe. And by the time that the CMB was forming, the dark matter would have become a lot colder than the atoms are, causing it to experience a lot less pressure than ordinary atoms do. And this would allow it to gravitationally collapse even on smaller scales. So atoms resist compression at this time if the overdensity in question is smaller than 200,000 solar masses. But dark matter overdensities could collapse even if they're much, much smaller. So you could imagine small clumps of dark matter forming that were like a millionth of a solar mass, or a billionth of a solar mass, or a trillionth of a solar mass, depending on, the details of the dark matter and exactly how they evolved in the early universe.
So it's not just that dark matter contributes gravity, which it absolutely does, but also because it's so cold and experiences so much less pressure than our normal matter that it has such a heavy hand in the formation of our universe's first structures.
Yeah, I'm fond of saying that it formed like the scaffolding that the visible parts of our large-scale structure would eventually be constructed around. So, you're building a skyscraper. Imagine that to build that skyscraper, first you have to, construct all this scaffolding around the construction site, and that makes it possible to build the skyscraper itself. If you look at a galaxy, what happens is the dark matter collapses first, forms a halo. That stuff then pulls in the atoms, forming the part of the galaxy we can actually see. Okay, so from what I've said so far, it seems that really big overdense regions should collapse under the effects of gravity exponentially, while smaller regions might resist this collapse due to pressure. And that's part of the story. But there's another important factor that I haven't talked about yet. In particular, it turns out that it's important that our universe is expanding. This has an important effect, or a very, very palpable effect, on the process of structure formation. In fact, what it does is it takes that what would have been exponential growth and it slows it down to something that's much more gradual. It still allows for the growth of structure, but not in this kind of runaway exponential rate. So once we take the effects of our expanding universe into account correctly, we calculate that clumps won't grow much for the first 50,000 years or so after the Big Bang. During this first 50,000 years, our universe's energy density was dominated by radiation, or particles that were traveling at speeds close to the speed of light. And under those conditions, these gravitationally, gravity doesn't really cause the overdensities to change very much. They change a little, but not very much in those first 50,000 years. But then once the matter becomes the main source of energy in our universe, the effects of gravitational collapse speed up. Not to an exponential rate that we got before when we ignored the effects of expansion, but still a lot faster than they did early on. So if we think about one of those regions in our universe around the time that the CMB was forming, 380,000 years after the Big Bang, that was 1 part in 100,000 more dense than average, after about 10 million years, it will be 1 part in 10,000 more dense than average. And after about half a billion years, it will be about 1 part in 1,000 more dense than average. So this just keeps growing until eventually these overdense clumps become gravitationally bound collections of matter that we call halos.
So I've always been a bit confused by the name halo to describe clumps of dark matter. To me, halo might evoke a few different ideas, maybe something like a ring or a disk, but really dark matter halos are roughly spherical clouds of dark matter.
It turns out that the smallest of these halos form first, and then the larger ones form a little bit later on. Galaxy-sized halos, for example, have been forming in our universe in large numbers ever since a few billion years or so after the Big Bang. But the bigger galaxy cluster-sized halos have mostly formed more recently in cosmic history.
Our universe is full of these invisible dark matter halos. And since dark matter doesn't experience as much pressure as normal matter does, these dark matter halos formed first in our universe, and then pulled in all the atoms with them. So the regions in our universe that are the most densely packed with the visible stuff, galaxies and galaxy clusters, these regions are also teeming with dark matter halos. So given that dark matter is invisible, we've never detected it, and we don't even know what it is, how exactly do we know that these halos exist, let alone how many there are and where they are and what shapes they are?
Some parts of the calculations that are involved in the process of structure formation can be done on paper, with real equations and notebooks and chalkboards and things. But it turns out that the final steps, the real collapse of these gravitationally bound structures into halos, isn't very easy to do on paper. You need to, use big computer simulations to do this, but we know how to do that, and a lot of smart people have done it. And using these simulations, along with these paper and pencil sort of calculations, we can figure out how many halos of different sizes and shapes should exist in our universe. And we can compare these predictions to the observations that we make with various kinds of telescopes.
Now, we aren't talking about traditional telescopes here.
When I talk about telescopes in this context, I'm talking about programs that are called cosmic surveys or galaxy surveys. This is very different from some of the more famous telescopes like, the Hubble or the JWST telescopes, these sorts of things. Those telescopes pick a target and they look really, really closely at it. They focus in on some direction and they look at something really small. In contrast, these cosmic surveys or galaxy surveys, they look at a huge, fraction of the sky. They might look at, tens of percents or more even of the whole sky over many, many, many nights or maybe even years of observation. And they don't look that closely. They kind of try to look at everything, okay? So they're trying to make a whole map of the universe and where all the galaxies are, not just in our local nearby universe, but as far back as they can. ideally, going back billions of light years in all directions. So one of the most important galaxy surveys was the Sloan Digital Sky Survey, which a bunch of people I work with at Fermilab were deeply involved with. And more recently, the Dark Energy Survey is kind of the successor to that program. And these are kind of the world-leading, galaxy surveys telling us about the large-scale structure of our universe. When we compare the observations of these and other cosmic surveys to the predictions that we made for the large-scale structure of the universe, we can learn a few really important things. First of all, what we see is, matches very well with the predictions of the theory. This didn't have to be the case. If the Big Bang Theory were, some sort of epicycle or some sort of mistaken premise or something, the large-scale structure of our universe would look different. This confirms the basic picture of how and why our universe has evolved, what it consists of, its composition, its history, its evolution, all that stuff. So we have one less reason to be suspicious of the Big Bang Theory because of these observations of large-scale structure. Second, we can use this data to help constrain how our universe has been expanding in detail over the past few billion years. Probably most importantly, this helps us to understand the nature of dark energy. So you may have listened to us talk about dark energy in other episodes of Why This Universe, but the basic idea is there seem to be a pretty large amount of energy in our universe that is causing our modern universe to expand at a faster rate, an accelerating rate than it would have otherwise. And by studying large-scale structure, we can, basically measure how it's been expanding and hopefully teach us as much as we can learn about the nature of this weird, mysterious dark energy. And then last but not least, the observed large-scale structure of our universe tells us a lot about the nature of dark matter.
Like I mentioned before, we've never actually detected dark matter and we don't know what it is. So physicists came up with many different ideas for what the sort of properties of dark matter could be. And one question was, how fast does dark matter move? AKA, is it relativistic? Does it move near the speed of light? So we call dark matter that's relativistic or moves near the speed of light hot dark matter. And we call dark matter that moves more slowly cold dark matter. And it turns out that by studying the large-scale structure, we could actually narrow down these dark matter theories.
These two different hypotheses, the cold and hot dark matter hypotheses, would form very different patterns of large-scale structure. In the cold dark matter case, the dark matter forms the smallest halos first. These might be these millionth or billionth or trillionth of a solar mass sort of structures. And then they tend to merge. They tend to form bigger halos by combining with each other, forming ever larger halos of dark matter, eventually forming things like galaxies and galaxy clusters. We call this process of structure formation hierarchical structure formation because it starts with the smallest things and kind of builds its way up. And then in contrast, hot dark matter isn't very good at forming small things. It has a lot of pressure, and that pressure makes it resist collapse on small scales. So it forms the biggest things first, and the only small stuff you get comes from the kind of fragmentation or the breaking apart of those big halos. So the net result is both hot and cold dark matter could explain the largest scale structure of our universe just fine. But when you look at the smallest things we observe, like the smallest galaxies, the things we call dwarf galaxies, there shouldn't be very many of those if the dark matter is hot, and there should be a lot more if the dark matter is cold. And it turns out from observations that there are a lot of dwarf galaxies in our universe, and it tells us the dark matter is pretty cold. Maybe perfectly cold, but certainly not anything cosmologists would call hot.
So it turns out the story of how our universe developed structure isn't just good for understanding the past, but also helps shed some light on the mysteries that we still don't understand fully, from dark matter to dark energy. Why This Universe is brought to you by the University of Chicago Podcast Network. It's edited and produced by me, Shalma Wegsman, and my co-host is Dan Hooper, a professor of astrophysics at the University of Chicago and Fermilab. If you like our show and you want to support us even more, you can find us on Patreon. There you can access ad-free episodes of the show, as well as exclusive Ask Us Anything episodes where you get to ask Dan and I direct questions about physics or anything else. So if you are curious about that, you can find it at patreon.com/whythisuniverse. Thank you so much for listening and for your support.